So in the batch calculation example, you have calculated saturation pressures using a variety of models for this set of melt inclusions from Soufriere Hills. And what we can do is we can expand this and we can calculate the saturation pressures using all models. And then we can plot these as cumulative frequency plots. And this basically shows stepping up the increase in saturation pressure with different melt inclusions until you get to the final melt inclusion in the dataset. What you can see is that magmasat, papale, Lu and volatile calc rhyolite all sit pretty much the same at about 10 kilometers depth, or about 2 kilobars. Volatile calc basalt and shishkina sit to about 4 or 5 kilometers deeper. And then the hydrous and the anhydrous version of Icona Marziano sit to way higher pressures. So say you end up with a result like this for your suite of melt inclusions. Obviously this is not ideal, that you can get pressures ranging from 2 to sort of 5 kilobars or 10 to 25 kilometers just based on your choice of model. So at this point you're going to want to start looking into why these models are giving different results and which models are most suitable for your situation. One way you can do this is to draw an isobar diagram. So what I've done here is I've taken the melt inclusion with the largest discrepancy between the models, just to give us the biggest differences. And I've taken the saturation pressure calculated for that melt inclusion using magmasat. And then I have drawn isobars using all of the different models. And this really allows us to visualize what the water and the CO2 solubility predicted by each model is doing. So what you can see is most of your melt inclusions are very water rich. So the thing that's most affecting their saturation pressure is how the models are handling water. And magmasat, Lu and volatile calc rhyolite, and even to an extent papale, all predict very, very similar water concentrations, and so does shishkina, which kind of intercepts down here. So you get reasonably similar saturation pressures for these. Shishkina is a little bit different, and then volatile calc basalt, which is offset to slightly lower water contents, is very different. The two Icona Marziano models predict about half as much water solubility as the other models, and this explains why you basically need twice as much saturation pressure. So down here, what we care about is how these models are handling water solubility. If your melt inclusions lay up here instead, you would suddenly start caring a lot more about how these models differ in CO2 solubility. So for example, while papale and magmasat are pretty similar for water, they are vastly different for CO2, and you may well want to look into that. And similarly, you can see Icona Marziano predicts way higher CO2, about 3 times as high as magmasat and Lu, for example. And shishkina predicts really, really low CO2 solubility. So you'd want to be looking into those differences. But here we're going to focus on why the water differs. And the easiest way to do this for the empirical models is to look at the calibration range. So here we are showing the NB/O value for the Icona Marziano calibration dataset against silica. And if we remember the expression for water solubility in this model, the only melt composition term is this NB/O value. And we can overlay the melt inclusions from this study. And what we see is that they lie to way lower NB/O values. And the constant that's been attached to NB/O means that lower values is lower pure water solubility. Now, should we really extrapolate this linear trend to such low values? In reality, we find that almost all of these empirical models go wrong when you extrapolate beyond the calibration dataset. So here we'd want to be very, very careful using this model, simply because it is so far from what it was calibrated on. Here's a very similar plot, but showing the differences in saturation pressure for different models for a suite of Kilauea melt inclusions. What we see is magmasat and shishkina lie to relatively similar pressure values, considering the errors on those models, and then Icona Marziano and volatile calc basalt lie to much higher pressures. So first, let's do the evaluation of perhaps why volatile calc basalt is giving different values. So here I'm showing yet again this pi silica trend that this model relies on. And we can overlay the post-entrapment crystallization corrected values of these Kilauean melt inclusions. Now what we see is that these triangular melt inclusions, these are ones which have undergone a lot of post-entrapment crystallization. They almost all have more than 49 weight % silica, so volatile calc is assuming that their pi value is constant. Whereas in reality, they actually have high and variable pi values as the amount of PEC decreases. So basically as the initial magnesium content decreases, their pi values drop, and yet we're assuming it's constant. and these values are far higher. So this means that the CO2 solubility will actually be higher than predicted by volatile calc, which would mean that we would actually need like lower saturation pressures to explain the amount of CO2 we measure. So it would shift it back to the magmasat line. So it's this simplistic relationship where we assume pi and silica follow the same trend as the North Arch lavas and then flatten out, that is causing volatile calc basalt to overestimate saturation pressures in this scenario. We can also look at Icona Marciano, and here we're showing the magnesium content versus the aluminum content. Their calibration dataset is shown in green now. The Shishkina calibration dataset is shown in black, and the fissure rate melt inclusions are shown in yellow, the kiloion melt inclusions. So if we look at how, say, magnesium and iron are parameterized in the Icona Marciano model, we see that this term is attached to a negative coefficient, and this means that as magnesium goes up, it's predicting that CO2 solubility is dropping. But in their paper, they say that this relationship really isn't very well constrained outside of 6 to 8 weight % magnesium, because that's where the calibration range is. You can see almost all of the green triangles lie here. So effectively, we're extrapolating this up to 6 weight % more magnesium than it's calibrated for. So we're bringing this value down, we're bringing the CO2 concentration that's predicting down, and therefore the model has to predict a high saturation pressure. In contrast, Shishkina is calibrated to these higher magnesium contents, and these are relatively similar in their aluminum contents as well. And magmasat contains the Shishkina dataset in its calibration dataset. So these are really the only models which are calibrated for these high magnesium melt inclusions, and it's kind of nice that they predict reasonably similar results within model error. Okay, so the other thing you did in that tutorial was calculate an isobar plot. If we just remind ourselves, an isobar plot basically shows the amount of CO2 and water that can dissolve at a given pressure, a given temperature, and a given melt composition as you are changing the fluid composition. So starting with a pure CO2 fluid, progressively increasing the amount of water in the fluid down to the right-hand side until you end up with a pure water fluid. So conventionally what people do is they take a melt inclusion composition, they calculate isobars, and then they overlay all of their melt inclusions onto that graph. But the problem with this is we have just been looking at how melt composition affects volatile solubility. And within a suite of melt inclusions, you may well have a wide range of major element contents. Say at Kilauea, we had magnesium contents ranging by about 6 to 8 weight %. So we plot one of these diagrams, say this is like the typical melt inclusion we've chosen to draw isobars with. And then we overlay all the melt inclusions on top. But if we were to have drawn an isobar for each of these red melt inclusions, say, rather than just a typical melt inclusion from this general suite of basalts, we can see that the spread of these isobars at a given pressure is actually pretty much the same distance between the 4 and the 2 kilobar isobar for a single composition. And this means we have to be very, very careful. Isobar plots can be very, very useful, but simply by looking at the position of these melt inclusions, we can't actually get their pressure out because the isobar that they correspond to depends on the major element composition of the melt inclusion. So here we can see this. We can take 4 of these red melt inclusions, just an example, calculate the 3 kilobar isobar for each, color-coded. So looking just at this plot, you might say that this red melt inclusion formed at the higher saturation pressure, and this one down here formed at the lower saturation pressure. Whereas in reality, the order isn't that simple. This green melt inclusion actually formed at the higher saturation pressure, 4.2 bars. The one lying above it forms at a lower pressure because of its major element content. So it might be better, instead of trying to plot things on isobar diagrams to visualize pressures, to instead plot something like water versus pressure in a water-rich system, CO2 versus pressure, or if you're working with, say, olivine, you might want to plot your saturation pressure versus, say, the 4-stroke content of your olivine. And this means we are calculating saturation pressures for every single inclusion, which means we're taking into account the fact that the major elements are going to affect our solubility calculations. And you can just see, here's an example. The previous one was using the Kone melt inclusions. This is using the Buttigieg suite. The same thing we see. Isobars from different melt inclusions span the range of entire, like, discrete isobars. And similarly for Kilauea, again, there is an awful lot of spread in the calculated isobar position. Okay, so now Simon's going to talk through some degassing calculations using VESIcal.